The purpose of this tape is to demonstrate to you the Petrographic microscope, to introduce you to all the parts and the terminology that are associated with the microscope. And so I'm using a Zeiss student microscope as a demonstration. There's a lot of variation in microscopes, but this one serves as well as any to demonstrate the different parts of the microscope. I'll start at the top with this removable bit of optics here, which is called the ocular, or the eyepiece of the microscope. And if we look at the eyepiece or ocular here, you can see that demonstrated on the top of the microscope is the symbol 8x. That indicates the degree of magnification that this ocular shows. Oculars have variation between, say, maybe 5 and 15x magnification. There also is an adjustment in the eyepiece, or the ocular, which serves to focus the crosshair. Most oculars contain a crosshair, some contain grids, and some contain micrometers for measuring the scale of that particular eyepiece. Another piece of the ocular is a small screw which serves to orient the ocular when it's put back into the tube of the microscope. This keeps the crosshairs in a north-south, east-west position, or keeps the grid or the micrometer oriented. So I'll put the ocular back in and move to the next bit of optics, and another very important part of the microscope, which is held here on a turret, are really a series of objectives, what we call objectives of the microscope. And these stick out in this position and can be rotated to the vertical position for alternative uses. Now, these objectives have different degrees of magnification. There's a high power objective, there's a medium power objective, and a low power objective that are traditional in petrographic microscopes. If we look at an objective closely, which I have one here, the typical kind of notation which they contain on them is they will show a power. This one is a 10x objective, and then there'll be a number following this, which in this case is 0.22. This is the numerical aperture, which I'll explain in a minute. There also are two centering screws on this objective. I've obviously removed this one from the turret just for demonstration, but these centering screws I'll also demonstrate their function and why we need them, but they're required to center the objective so that what we're looking at remains in the center of the field of view. And you can see also that there's a screw fitting where the objective screws back into the turret of the microscope. Well, the normal complement of objectives on a microscope includes a low power objective, which in the case of the Zeiss microscope is typically about 2.5x, and that's an indication of the magnification that it provides. A medium power objective, which has about a 10x magnification, and a high power objective, which is 40 times magnified. And you can get a rough index of the total magnification that a microscope is providing by multiplying the magnification of the objective times the magnification on the ocular. For example, in this particular case, for our medium power, which is a 10x objective, multiplied times the 8x ocular, we have an approximate total magnification of 80x. Now, there's another property of the objective that we need to worry about, and it's shown really by this graphic. And here I've taken a side view, and you can imagine this slide, it's indicated as a slide here, as being the plane of the microscope stage where our specimen is located, and I just put the object which we're viewing here as a point on top of the slide. And then graphically I've shown here the point of the objective with the lens in the bottom of the objective. And this diagram is meant to show that there is an angular relationship that can be defined as to how divergent the light can be coming into this objective. And this angle, that is the angle between the divergence of light that's possible in the objective, is called the angular aperture. So each objective has an angular aperture as well as a magnification, which in this case is a 10x. And there's another thing that is very important in terms of the operation of the microscope, and that is how much distance you have between the end of the objective and whatever you're looking at. And this is called the free working distance, or FWD abbreviation. Now the free working distance changes depending on what objective you're using. Well, here's the relationship between the angular aperture, or abbreviated as AA, and the numerical aperture. And the way we make this relationship is we talk about an angle called U, which is half of that angular aperture angle, and we describe the numerical aperture in terms of the sine of that angle U. So the numerical aperture is the sine of the half of 1/2 of the angular aperture of the microscope. And each objective will typically be described by its numerical aperture and its magnification. Now, this next graphic shows the relationship between the magnification that is typical and the angular aperture and the free working distance. So let me describe this as these objectives are typically balanced, and they come from the turret located here, and the distance that they have between the turret and the stage is usually balanced so that you can rotate your 40x objective in and your 10x objective out, and you don't have to change the distance of your specimen to the turret by a very large factor. So there's a systematic relationship. As you're using high magnification, you have very small free working distance. As you're using low magnification, you usually have a much larger free working distance. And this is the normal relationship of the objectives. And you can also see that the angular aperture for this high power objective is generally larger than the angular aperture for the low power objective. In order to quantify this, I have another tabular summary here which describes the low, medium, and high power objectives and the actual physical amount of free working distance that we're dealing with. That is, typically with a normal kind of low power objective and a petrographic microscope, we have about 35 millimeters, or very large free working distance. There's a big distance between the end of the objective and the specimen. And this distance becomes much smaller for a medium power objective and extremely small for a high power objective. This can be a real danger because it's quite easy sometimes to puncture your specimen with a high power objective just in the adjustment of focus, that is the changing of the position of the stage. So you have to be real careful using your high power objective because you have a small free working distance. Now the other thing I showed here is something called DOF. What I mean by that is the depth of the focus. And this is how much vertical section of the specimen is actually in focus. The depth of focus is very large, 1/2 millimeter in your low power objective. That means that your whole specimen, your whole thin section, frequently can be in very good sharp focus when you're looking at the low power objective. Now the depth of focus becomes much smaller and finally very, very small, much less than the thickness of a normal thin section or any kind of preparation, mineral preparation for your high power objective. And so the focus becomes very, very critical, and you can move up and down within the specimen. Okay, I'll look back again at the microscope and go to the next portion of the microscope that concerns us, and this is the actual focusing adjustment. And the focusing is controlled on the microscope by actual and physical, in this particular case, by movement of these knobs. There's a rough focus, which makes a very strong movement, and there's a fine focus knob, which adjusts the level of the stage very slightly. If I move this very rapidly, you may be able to see the actual movement of the stage itself. Now it's lowering, and now the stage is actually rising, decreasing the free working distance. But obviously you have to move the plane of the stage until it's you get a properly focused image for the microscope. So we have a coarse and a fine focus. The next thing I want to show you is the stage of the microscope. Obviously this is where you put the specimen, the microscope on. And the stage has the ability to be rotated. And this is a very important property. And furthermore, you can control the rotation because there are actual graduations that occur, and every angular point is graduated and numbered on the microscope. And you can lock the stage so that it can not be moved or rotated as well by using a set screw on the side of the stage. Now, we also have special aids that a lot of times we use the stage directly. We can put the specimen directly over the hole that occurs in the center of the stage and look at the specimen this way. But we also have special devices that help us orient a specimen. Now I'll show you one of these. This is a mechanical stage which you can position right on the microscope stage, and it has two screws in it which allow movement of the individual specimen in this sort of way. And there are graduations on these so you can precisely position any specimen. The thin section can be placed right in between these clamps, and you can rotate these screws so that you can precisely orient any sample and reoccupy any position within that slide very, very precisely. Now, most of the time that we're using the petrographic microscope, we don't use this mechanical stage, but during special kinds of orientations, we do use it, and it's a very, very useful device. Okay, the next thing I want to call your attention to is lighting of the microscope. And for lighting, we start with typically a tungsten light source. Here's a tungsten bulb which provides the primary light. Now, lighting is obviously critical for the specimen. If you're going to see it well, you have to have very good lighting. And so these are usually high-intensity tungsten bulbs. And the bulb is placed actually inside the microscope. And you can see the cord emerging from the microscope in this position. And the bulb is located here, just below this opening. And there's a switch on the side of the microscope to regulate and turn the light on. Some microscopes actually have mirrors which to do this, but I think as you see, as I turn the switch on, you can see the light opening up there, and you can see light emerging in this position. And it goes through this hole and is directed directly upward toward the specimen, and then through the objectives and out the eyepiece. Now, every light has a diaphragm, and you can see changing the side of the diaphragm here, which controls how divergent the light is coming from the source. This is an important variable that you'll want to change. There are other diaphragms elsewhere in the microscope, but there's typically one right associated with the source of the light itself. And there's also a filter which is commonly used, and this we use because the light typically coming from a tungsten bulb is colored. It's somewhat yellow, and so we use a blue filter which corrects the light so that it is very close to white, or relatively balanced right across the spectrum, so that we have white light shown and we don't have a bias toward yellow wavelengths. Typically now when we're looking at specimens, we use white light, and we use this blue filter to help us. This white light is, of course, light of a whole variety of wavelengths. But there are some times when, using the petrographic microscope, we need to look at light of only one wavelength. And in order to do this, we use a device called a monochromator. I have a monochromator here. It's actually a very simple device. It starts again with a bulb, which is located here on this side of the instrument, and the bulb, and there's an opening coming from the bulb which shines a directed beam of light into this part of the instrument. This part of the instrument is really a grating, and the grating is designed to separate wavelengths of light. And so there's a graduation here which shows different wavelengths, and I can set this on 640 nanometers, which would be in the red light range, and I can go more toward violet light passing through yellow light in the middle of the range around 500 nanometers and going toward our violet wavelength. And so having this grating control is important because I can take the white light and split it up into its various wavelengths. Then the light emerges out the other side of the monochromator, out this side, and goes toward the microscope where it's directed by a series of mirrors. So a monochromator has a very special kind of application when we want to look at only one wavelength, or monochromatic light. We use the monochromator as an aid. Okay, I'll go back to the microscope and look at some polarizers. This is a polarizing microscope, which tells you that it has polarizers. And I'll just locate these. The first one of these is located below the stage in this position. It flips in and out, but in fact, in using the petrographic microscope, we always have this polarizer in. It's possible to remove it for cleaning, but in fact, we never look at a specimen without this polarizer present. Now this polarizer has a specific orientation, and I should be clear about this, but the orientation of polarizers uses a common kind of notation. So in order to do this, let me just place the microscope in a reference position like this. And this is the way you would normally look at it. And so if we can look at this microscope in terms of the microscope stage, then this direction, the way in which my hand is pointing, is arbitrarily called north. It may or may not be north where you're sitting. And the direction across like this is an east-west orientation. This is a north-south orientation. Now the polarizer that's below the stage in a Zeiss microscope is always east-west. That means that the permissible vibration direction of light as it comes up toward the stage of the microscope is only in this east-west direction. Now above the stage of the microscope, in this position, right here, there is another polarizer. This polarizer is called the analyzer, and it's got a lever device on it, a pull device on it, which makes it very easy to put it in and out. So it flips in and out very readily. And that's symptomatic of the fact that you are all the time, when you're using the petrographic microscope, putting this analyzer in and out. So this upper polarizer is called the analyzer. It flips in and out, and you look at specimens both with it and without it very commonly. Now, the upper polarizer, or the analyzer, by convention in a Zeiss microscope, is always got its polarization direction in a north-south direction. Okay? So when we have this upper polarizer in, then we have a polarizing screen above the stage oriented in this direction, a polarizing screen below the stage oriented in this direction. East-west, below the stage, north-south, above the stage. This is a convention adopted by Zeiss microscopes. What you find is if you have another brand of microscope, this might be reversed, and you should try to find out which way your polarizers are. If it's a Zeiss microscope, it's certain to be east-west below and north-south above. And it does make a difference in some optical tests. Okay, the next thing I want to point out to you is something that's found below the stage of the microscope. This is the substage assembly of the microscope, and it's located right in this position here, just below the microscope stage. Now I've taken one out of another microscope which I can show you quite readily, and so I have it right here. This fits just above the rest of the substage assembly, and it really consists of two parts. There's a lower part below, which includes a lens and a diaphragm, which again you can direct the divergence of light in this sort of way. And there's an upper part which is called a converging lens, and this lens flips in and out, so you can have it either out of the field of view so that the light from the microscope source passes right through to the stage without interference of the converging lens, or you can flip this converging lens in which case the light is directed, and so that it forms a conoscopic kind of array. Here the light goes straight through the specimen, here the light goes through the specimen in many different angles. So this is the substage assembly consisting of a diaphragm and a converging lens, and fits below the microscope stage. Now there are two main ways to operate the petrographic microscope. And the first way that I'm going to talk about is orthoscopic view. Now orthoscopic view is perhaps the most common way that we look at specimens. In orthoscopic view, we operate without both the Bertrand and converging lenses. I'll show you the Bertrand lens in a second here. We also operate either in plain polarized light, that means with just the lower polarizer in, or sometimes we operate with what are called crossed nickels. Crossed nickels are polarizers that are crossed, that is with both our east-west polarizer below the stage and our north-south polarizer above the stage. So let's set up the microscope now for orthoscopic view and take a look at what orthoscopic view looks like. Here's a microscope here. I should show you one last part of the microscope, which is located up here on an upper control here. This is a control of something called the Bertrand lens. The Bertrand lens is a lens very similar to the converging lens that's found below the stage, which flips in and out using a knob here in this location. And we use the Bertrand lens in conoscopic view. We do not use it in orthoscopic view. So if we set up for orthoscopic view, we have our specimen, we have our Bertrand lens out, we have our converging lens located below the stage, also in a in and out position. So we get our microscope set up this way. We'll take a thin section, put the thin section on the stage of the microscope, and take a look at this thin section using our medium power lens. Now this is a specimen of granite taken in thin section, and if you look closely you can see grains of biotite and hornblende. This is what orthoscopic view is good for. You can see actually the outline of physical materials in the specimen. You can look at the percentages of minerals, you can look at the color of minerals by viewing them in orthoscopic view. Now in this position we have we're looking at the specimen in plain polarized light, which means only the lower polarizer is operating. Now watch what happens to the field of view when I put in the upper polarizing screen. Now the specimen is viewed in cross-polarized light. You can see that the overall level of light is much less, but the minerals are still illuminated, and we can test different kinds of optical properties in cross-polarized light. So again, orthoscopic view in plane polarized and crossed polarized light. Just a demonstration of a common way of viewing materials. Now the other way we look at specimens is called conoscopic. And conoscopic is different very fundamentally from orthoscopic. In the first place, it's different in terms of the way we operate the microscope. Always in conoscopic view we're using crossed nickels. Generally also we're using a high power objective, although not always. But we always use crossed nickels, and we use both the Bertrand and the converging lenses. And the purpose of those lenses is, instead of allowing light to go straight through the specimen, these lenses allow the possibility for very divergent light to go through the specimen. Now the result of this is quite surprising, because now we don't see mineral specimens at all, but we see very vague looking features called interference figures. Now let's set up the microscope to look at an interference figure so you can see what that looks like. Here again, I'm just taking a very large specimen of biotite, putting it on the microscope stage, and I'll rotate to my high power objective, and I'll put in the Bertrand lens and the converging lens into the field of view, and usually turn my light source up nice and high, and take a look at this interference figure that we're seeing in conoscopic view from the mineral biotite. So this is a very different fundamental way of testing optical properties of different minerals, and we'll get to know all different kinds of interference figures tested with the conoscopic method of observation of the microscope. Okay, next I want to talk about some special devices called accessory plates. And I have a few of these here to show you. There actually are three kinds of accessory plates. Two of them look very, very similar. These are the first two of these. This one is called a gypsum plate. Gypsum plate is also, if you look closely here, you can see the little letter lambda. Lambda stands for one wavelength of yellow light in this particular case, because the lambda that's referred to is exactly 530 nanometers. We'll learn what that means, but that's essentially one wavelength of yellow light. That's what it corresponds to. So it's called a one lambda plate, or a gypsum, very commonly a gypsum plate, and that's because the material that is actually in the accessory plate is made out of gypsum, and you can see this transparent portion of gypsum here. Another important thing about these accessory plates is they typically have a line on them, and you can see this line going across. That line is very important to notice, because some accessory plates have this line oriented across the plate, and others have them oriented along the plate. You should be aware of what your accessory plates say. More conventional way is to put the slow direction across the plate like this, and this is what these two plates show. They have their slow direction, or the line of orientation that's located on them goes across the accessory plate, and this is something you want to notice. This other kind of accessory plate here is called a mica plate, or quarter wave plate sometimes. There's a symbol lambda over 4 on this plate. Sometimes if you will see the word glimmer on this, which is a designation for mica plate if it's of German manufacture. So lambda over 4, quarter wave plate, mica plate is another very common kind of accessory plate. Well, what do we do with these plates? In order to see what we do, I'll put the microscope back up here and show you an accessory slot, which is located right here in this position of the microscope. And the accessory slot being located right here, you can slide the accessory plate right into the accessory slot and to the position above the stage, so that the mineral that's found there actually intersects the light source of the microscope. So we take these accessory plates and slide them into the accessory slot like this, and we'll be doing optical tests making that manipulation. Now, a third kind of accessory plate is called a quartz wedge. See, it looks a little bit different than the gypsum and mica plate. It has a very elongated piece of quartz located here, which is very thin at one edge and very thick at the other edge. And this is operated in the same way. It's slid into the accessory slot of the microscope. Another thing to notice about this particular quartz wedge is that the slow direction on this quartz wedge is indicated to be along the direction of the quartz. That is, the slow direction goes along the quartz wedge. And this is against most of the convention. This one happens to be made in Britain, and many British accessory plates have their slow direction along the accessory plate. Most accessory plates made in other countries will have their slow direction across the accessory plate, and you should very carefully notice on your accessory plates the position of the slow direction, because it will make a difference in the optical tests. And the quartz wedge is used by sliding into the microscope slot and watching the dynamic changes that you can see within the microscope as you insert the quartz wedge. Well, what are some different kinds of preparations that we look at on the microscope stage? Let's look at a few of these. The most common type is something we call a thin section. And I have a thin section here. Shall be showing you here. The thin section preparation looks like this. It's a very thin section of rock. In fact, it's so thin that the material is transparent. You can see my finger beyond them. Some of the minerals are a little bit more colored than others, but you can see right through. So the rock has been ground so thin that it's possible to, it's effectively transparent. So we're using transmitted light in the petrographic microscope, and we can actually see through the minerals in this rock. It started out, the specimen started out looking like this. This is essentially just a slab of rock. You can see the different minerals in the granite. It's been cut with a special saw, and so that we have an orientation here. And we're going to take this specimen and prepare it. If we're going to prepare it into a thin section, then we need a glass slide like this right here, and we simply glue the rock specimen onto the glass slide like that as a start in terms of the preparation procedure. Having a very smooth surface here, and we use an epoxy to glue it on. There's in fact a little layer of epoxy between the rock and the slide itself. This material is glued right onto the glass slide, and then we begin to grind this surface until it becomes thinner and thinner. And here's another example. The same rock now has been ground to a very thin thickness. It's less than a millimeter thick now, but still it's opaque. You can't see through it at this particular stage, so it takes a bit more grinding still until you get the transparency that we see in the final thin section. The other thing about this final thin section that you can see is that there's a cover glass that makes the top surface very, very smooth on the thin section, and that's been placed over the very thin rock slab, and there's been a mounting medium applied to this, or an epoxy, or some material which we call Canada balsam, which essentially glues the cover glass to the rock specimen. So we have a very smooth upper surface, we have a smooth lower surface from the glass slide itself, very thin rock specimen, and a kind of sandwich in between layers of epoxy. This is a normal preparation of a thin section, and it's the standard way really to look at the mineralogy of rocks in transmitted light. Now, sometimes we want to make examination of minerals in which we can actually change the index of refraction of the mounting material. In a thin section, the material we use is usually called Canada balsam, or sometimes it's an epoxy, but it has a fixed index of refraction. It always has the index of refraction of 1.54. But sometimes we need to look at mineral grains which have a different index of refraction. And so when we do this, we can prepare a special kind of mount which we call an immersion mount. And I have the materials to prepare an immersion mount here. In an immersion mount, here we can see the materials here. There's a specimen here of a sample which is very finely ground powder of a mineral grain here, and I can use this spatula to extract some of these mineral grains, as you can see that I've done. You can see the vague white forms here, and I put them on a glass slide together with a tiny cover glass. This cover glass then is meant to control the upper surface of these particular grains, so I can manipulate these grains so that they're covered largely by the cover glass in this kind of orientation. And then I take a liquid and use a little dropper for the liquid, touch the dropper to the edge of the cover glass, and the liquid is actually pulled into the space between the cover glass and the glass slide. And this is the making of something called an immersion mount. Now those mineral grains are bathed within an immersion liquid, and this immersion liquid can have any index of refraction that I wish, because I can take different index of refraction and prepare them. And this is an immersion mount, another very common way of looking at mineral grains of some particular kind of composition. I have an example here of a bottle of this immersion liquid. Normally you have a whole fleet of these bottles. Here's our bottle of index of refraction liquid, and you can see that it's labeled right here with a number 1.462, which represents its index of refraction. There also are some other numbers which correspond to temperature and wavelength corrections of the index of refraction. Now we can actually measure the index of refraction of an immersion liquid in the laboratory. And to do this, we use a device called an Abbey refractometer, which I have right here. This is what the Abbey looks like. It's looks a little bit like a microscope. There's a viewing tube here, which has an ocular in it, but there's a chamber here on which there are two smooth surfaces, or prisms, and it's on this surface that you can put a drop of your immersion liquid right here in this location to close the Abbey in this position, to have a light directed in this side of the refractometer, which causes refraction to occur, and then you look down the tube and focus the refractometer to directly determine the index of refraction of any particular liquid. And you can never trust the labeled index of refraction that's found on a particular index of refraction liquid. You should check these things repeatedly, because they evaporate and the index of refraction changes. Okay, well, let's do a few simple optical tests now with our microscope. The first thing I want to do is to calibrate the field of view. In order to do this, I'm going to use a special preparation called a micrometer slide. This micrometer slide, you can't see this, but there's very small graduations, 2 millimeter long graduations at 1/100th of a millimeter that are in the middle of this slide. And I'm going to take this slide and place it on the stage of the microscope, and to look at this particular slide using our different objectives. Okay, so here, for example, is our low power objective, and what I'd like to do is to measure the distance between the center of the field of view and the edge of the field of view using this micrometer slide. So I'll just position the micrometer slide so that it's located one end at the crosshair, the other end at the edge of the field of view, and measure, finding it's approximately 2 millimeters here from the center to the outer edge. I've now calibrated the size of the field of view for my low power objective. Now I'll move to the medium power objective, make the same kind of a measurement. In this particular case, I can see again, measuring from the center of the field of view to the edge, a distance of 0.55 millimeters represents the scale of my medium power objective. Now I'll go to the high power, again make the same measurement. Now the graduations are getting quite large, as you can see, and that the distance from the center to the edge of the field of view is approximately 0.14 millimeters. These will be different on different microscopes. You should measure your own field of view on your own microscope and keep this as a reference so that you constantly know what the scale is of materials that you're looking at. Okay, second thing I want to do is to demonstrate how one centers an objective. In order to do this, I'm going to put my granite thin section back on the stage of the microscope, and to look at this granite thin section again with my medium power lens, and here we are looking at it in orthoscopic view. I'll rotate the stage here, and you can notice that this particular rotation shows that the slide is not at all centered. In fact, there's a biotite grain that has the center of the field of view that's located way in the northwest corner in this kind of position. Now I'm going to move the centering screws. Remember their position on the objective itself, and I'm going to move these centering screws until that biotite occupies the center of the field of view. That is coincident with the crosshairs. And now I can show you that with rotation that this objective is correctly centered, and I'm ready now to use that objective. Both your medium and your high power objective should be centered each time that you sit down at the microscope. Now one final adjustment before we're ready to use the petrographic microscope, and this is to check the position of the polarizers. The polarizers can be moved in many microscopes, and it's important to know that they are exactly in a north, south, and east-west position when you begin examination. In order to do this, I'm using a mount of a mineral called Naturalite. Naturalite is a nice elongated mineral grain which is elongated in such a way that it becomes dark in cross-polarized light at a time when it is exactly parallel to cross-polarizers. So here we can see the Naturalite grain, and as I rotate, you can see very clearly that extinction or darkness on this grain in cross-polarized light occurs when the mineral grain is precisely east-west or north-south. If this were not the case, then you should adjust your polarizer in such a way that it becomes precisely north-south and east-west. And now then you're ready to look at petrographic specimens with the petrographic microscope.